Let's see. All right, guys. So today we're going to do section 10.1. As you all know, we got this midterm coming up. I don't know, any questions before we get down into the math? Everything's good? All right. So on Friday, I was doing improper integrals. There's a couple examples which I didn't get to, which I would have done if I had had time. I would have talked about a few kind of neat examples of improper integrals, like was it the gamma function I was going to do, or another thing called the horn of Gabriel. So since I didn't have time to talk about those, I did put them in the review outline for the midterm. I encourage you guys to go check those things out, and if I do have time, I will talk about it, maybe today or on Wednesday. But for now, let me just do what I have to do to be on schedule, which is 10.1. Okay, so I think I'll introduce this topic the same way I introduce all my favorite math topics, which is relating it to pizza. Okay? Because, let's see, as you guys know, pizza is the best food in the world. I did have pizza for dinner last night. Totally had a mushroom pizza for dinner last night. And okay, so we've done questions about slicing up pizza before. So I'm going to ask you another one about slicing up, how to slice up a pizza in a fair way. And by fair, I mean, you don't want to be that guy that takes the last slice of pizza, right? Like, I remember when I was like 15, me and some friends, we had gone to Domino's or something, and there were only 3 slices of pizza left, but it was like one big one and then 2 really skinny ones, and no one was taking either. We all wanted to eat the rest of the pizza, but no one would take either the 2 skinny ones because we all wanted that one big one. And then finally I was just, screw it, I just separated the 2 little ones off and took the big one. All my friends were pissed at me. It was great. So let's say that's the question now, is like, you've got this pizza, and first you cut it in half. And then you eat the bottom half. The bottom half of the pizza is gone, okay? So you now have half a pizza left. And once again, you don't want to be that person that eats the last slice, so you slice it in half, and then you eat that piece. So now that piece is gone. And maybe you can see where I'm going with this. For the next slice, you again slice it in half, eat that piece, and now this is the amount that's remaining. So you started off by eating half of the pizza, then you ate a quarter of it. Let's see, what fraction is this left? That's an eighth of the slice of the whole pizza. And the reason that I bring this up is because this is the sort of motivating example that I want you guys to keep in mind for this and the next section, which is if you keep on slicing the remaining piece in half and eating that piece, so the next piece would be a 1/16 of a pizza. First, how many slices is this total? Well, so I wrote down 4, but if I keep on doing this, this is an infinite number of slices of pizza, because you can keep on doing this indefinitely, right? You can always, however much is left, just slice that in half. However much is left then, just slice that in half. And you're never going to have no pizza left. So the first piece looked like this, the second piece looked like this, the third piece looked like this, the fourth piece looked like this, and these pieces are getting really, really skinny, kind of like the ones that I didn't want to eat when I was sharing it with my friends. But the point is, that's an infinite number of pieces. But altogether, you can see this infinite number of pieces, even though it's an infinite number of slices, which might sound like a lot of pizza, altogether, it made up exactly one whole pizza. And what we're going to be doing in this and the next section is building up the requisite mathematical background and rigor to justify that statement mathematically. To do that, we ultimately need to talk about series, but to do that, we need to do sequences. So today, let's start on sequences. What is a sequence? I mean, this is, I guess, the 20 series. That's a sequence, Math 20 sequence. In general, in math, a sequence is a list of numbers. Specifically, though, it's an ordered list of numbers. So, I mean, if you just have a list of numbers without an order, that's just called a set. But when you assign an order to them, that's called a sequence. And by order, I mean there's a first term, there's a second term, there's a third term, and a fourth term, and so on. So usually, the notation that we use for them is we'll just use a little index subscript to indicate that this is the first term of the sequence, this is the second term, this is the third term, the fourth term, and then the dot, 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 which, by the way, who knows what the name for a dot, dot, dot is? An ellipsis. The ellipsis means continuing on in the same fashion. Is there anyone here for whom sequences are new material? Okay, good. I made sure to do them in my pre-calculus class, so I think this should be a review. At least the first part of this lecture should be review. So let's do some examples. Oh, okay, well, before I do examples, do sequences go on forever, or do they stop? It's kind of a matter of definition, but for our purposes in this class, they will always be infinite. Sequences always go on. There's always going to be an infinite number of terms. So for this class, sequences are infinite. Now, usually the sequences are going to have some pattern, maybe a formula. But even if they're random, that's okay. It's still a sequence, even if it's random. So they can be random. Or non-repeating. Or they can just repeat the same number over and over. Or constant. So, here's some examples. Like the example that I started off the course with, the pizza slice example, was 1/2, 1/4, 1/8, and so forth. How about one that just alternates? 1, -1, 1, -1, so forth. How about 42, 42, 42, 42. This is going to be my example of a constant sequence. How about 3, 1, 4, 5? Any guess? 9. Good. All right. Yeah. So the person who guessed 9, who is that? What's your name?
Jerry.
Jerry. Yeah. Jerry guessed 9 correctly because he recognized these are the digits of pi. Now, since pi is an irrational number, these digits go on forever, and they never repeat, and there's never a pattern. Oh, I'm missing. Sorry. 3.14, is that what you were going to say? What were you going to say?
I was going to say it was like the Fibonacci sequence.
Oh, okay.
Last two terms.
We'll get to that. This one, this was supposed to be the digits of pi. I meant to do 3, 1, 4, 1, 5, 9, and so forth, which you might recognize as the digits of pi. The reason I wanted to mention this example is just to show that you can have sequences that go on and there's no pattern ever. You could not find a pattern or formula for these digits. But since you guys mentioned Fibonacci, let's do that one. So, and anyone not know the Fibonacci sequence? Okay, good. So how about I just start writing some terms, and let's see if you can figure out what the pattern is. The first two are always 1 and 1 for Fibonacci. Okay, so next one is 2. What's the next one? 3. Who is one of the people that didn't know? What's your name? Adrian. I'm going to tell you the next term. It's going to be 5. Can you guess what the next one after that is?
8.
Nice. Okay, and who else didn't know?
Julia.
Nice. All right, cool. So you guys see the pattern? I bring up the Fibonacci sequence for a few reasons. For one, it's the first sequence that I've given you that has to be defined recursively. So in the case of the Fibonacci sequence, in fact, the definition is given in terms of the previous 2 terms. You simply add up the previous 2 terms. So to get the nth term of the sequence, you take the previous term and the term before that. Now, let's see, while we're practicing getting formulas for these terms, let's get some formulas just as practice for the other sequences that I put up here. So how about for the first example, the pizza one? If this is a 1, and this is a 2, and this is a 3, then an is what?
1/2 to the n.
All right, yeah, 1 over 2 to the n, or 1/2 to the n. Okay. How about, does anyone know a formula for this alternating sequence? What's an for this alternating sequence? Some people might do it in terms of cosine. That's you could write it as, let's see, -1 to the n plus 1 would work. You could also do cosine of n pi, or negative cosine of n pi. Yeah, they're both equivalent. These are the exact same thing. You should check that if you didn't already know it. This one's pretty easy. A1 is 42, A2 is 42, ... AN is also just 42, the constant equal to the answers to life, the universe, and everything. If you ever read Hitchhiker's Guide to the Galaxy, you know what I mean? This one, I've got no hope of writing a formula down, so I'm not even going to try. Fibonacci sequence, I gave the recursive definition for. And let's talk a little bit about Fibonacci, because it's kind of cool. I just posted some more extra credit YouTube videos for you guys to watch on the Fibonacci sequence. I'm glad you guys like those. They're pretty short, and so the reason, a lot of mathematicians like to talk about the Fibonacci sequence as an example of the beauty that can be found in mathematics. It's actually very closely related with the so-called golden ratio, which some of you might have heard about. So that, for those of you that maybe haven't or don't really know much about it, I thought, if you go and watch some of these videos on the Fibonacci sequence, you might see some cool stuff that maybe you didn't know about. In particular, so these numbers appear all over the place in nature, which is one of the kind of crazy things. Like almost any time you have spirals, say in sunflowers or in snail shells or shells of shellfish, I guess, in the branching of trees, even in flight patterns of birds, Fibonacci sequence just sort of pops up in all these different disparate areas of science and biology, and even in music, as you will see in one of the videos I sent you. Although I'm not super convinced about the music, you guys will watch the video. You can decide for yourself if you think the Fibonacci sequence really appeared there or not. Sorry? No, although I saw that, I was thinking about checking out that video. I did not. The example that they use is Chopin, and also Bartok and Debussy. But I'll have to check out that Tool video too. Anyway, so let's get on to some new stuff that maybe, even if you've seen sequences before, if it wasn't in a calculus class, you may not have learned about convergence of sequences. So this should remind you of limits. So here, we say a sequence converges to L, and we write limit of the of AN is equal to L if, and this should remind you of your limit definition from the beginning of calculus. For all epsilon, epsilon greater than 0, there exists a natural number n such that an minus L is less than epsilon for all indices n bigger than the capital N. So it's kind of a tricky looking definition, but all it means is eventually the sequence gets very close to this number that I'm calling L, the limit L. So pictorially, let's imagine this is the index n axis, and this is so I'm going to graph y equals an, and maybe the first two terms will bounce around a little bit, whatever. But eventually, they need to settle down at one value. So in this case, it looks like if this is my limit L, then this looks like this sequence eventually settles down at that value L. And what the definition means is that no matter how close you need me to get to that number L, I can get there. Like epsilon, which you should imagine is a very small number, as it usually is. We usually reserve the letter epsilon for very small numbers, and that's what you should think of it as. And you might be asking, how small? As small as you want, as small as you need it to be. Maybe 1 billionth or 1 zillionth or 1 trillionth or maybe 1/2. It's as small as you need it to be, and however close you need to get to that limit value L, so within L plus epsilon and L minus epsilon, eventually all of your sequence values are within this band, this epsilon band of the value L. That's what this definition means. So here's an example of that. How about if AN is the sequence n plus 3 over n plus 1? Then let's calculate. So A1 is 4 over 2, which is 2. A2 is 5 over 3. A3 is 6 over 4. What's that? It's 1.5. A4 is 7 over 5. What's that? 1.4. Let me try plotting some of these. Okay, so we started off, the very first one was 2. And then, let's see, A2, what is that? It's like 1.6 or something. 1.5. 1.4. Let me just, how about, what's A10? That's 13 over 11 is like 1.2 or something. 2, 3, 4, 5, 6, 7, 8, 9. So without spending all day here, what's the value that this sequence looks to be going towards? It's supposed to be going towards 1. So yeah, I don't want to plug in all these numbers, but if I did, they should be getting very close to the horizontal line at 1. And maybe you could tell by looking at the formula that this sequence approaches 1. Hopefully you can tell by looking at the picture that it looks like it's approaching 1. But let's prove it like if this was a proof question. So from the definition, prove that the limit as n goes to infinity of n plus 3 over n plus 1 equals 1. And here's how you do a proof of this. So I'm going to evaluate the difference between an arbitrary term in the sequence and my limit L, which is 1. Let's look at that. So an minus L, or n plus 3 over n plus 1 minus 1, is equal to n plus 3 over n plus 1 minus, let's get a common denominator here. Okay, so this is n plus 3 minus n plus 1. Let's see, the n's cancel out. 3 minus 1 is 2 over n plus 1. Okay. what is it that I want? Is I want this quantity to be arbitrarily small. So we're going to let epsilon just be arbitrary. We don't know what it is. And what I want is for this quantity to be less than epsilon, at least according to that definition. So this takes a little bit of calculation. We want 2 over n plus 1 to be less than epsilon. But n, by the way, is positive, so this is the same. I don't need the absolute value. So let's see. If I divide both sides by epsilon and multiply by n plus 1, I get n plus 1 greater than 2 over epsilon, i.e. n greater than 2 over epsilon minus 1. So as long, okay, so here's how this works. Is you suppose you chose this number epsilon that it's given to you, and it's a very small number. You don't know what it is, but it's fixed. It's chosen. Now, whatever that number epsilon is, 2 over epsilon minus 1 is presumably a big number, right? Because if epsilon is small, then 2 over epsilon is big. And as long as your index is larger than whatever this number is, the inequality that an minus L will be less than epsilon will be satisfied. So think through that logic again if you have to. As long as I pick my number n bigger than whatever this quantity is, I satisfy the necessary inequality, meaning I'm within this epsilon band of my limit value L. So it's done, right? So then for n bigger than 2 over epsilon minus 1, an minus L is less than epsilon, and it's proved. By the way, mathematicians like to put these little boxes at the end of a proof. Means like it is proved, or the proof is done. I don't know how familiar you guys are with proofs, but yeah, this is a little taste of what you would do in Math 142 or 140, which is Introductory Real Analysis and Real Analysis for Poets. Okay, they don't call it for poets, but it's like the easier version of the analysis. Anyway, okay, so what is coming next? You might want to, in terms of this last example, looking at this formula for an, it might kind of remind you of the function. So like, think of the function f of x equals x plus 3 over x plus 1. Right, it's kind of, how should I say this? This function, if this is f of x, then f of n is an. Right, so if you want to derive properties of the sequence, sometimes it just suffices to just look at the function defining the sequence. So that's a general property. So in general, if an, you can write some formula for it. It's some function of n. Then looking at the limit of the sequence, as n goes to infinity, that's the same as just looking at the limit of the function, f of x, as x goes to infinity. It's the same thing. So my point was, if we had just looked at the graph of y equals f of x equals x plus 3 over x plus 1, that graph would just basically smoothly connect all those dots, and for the behavior at infinity, we could have just as easily been looking at the function as well. All right. I have to time this lecture out correctly. Not sure if I'll be able to fit all this stuff. Okay, so I'm going to give you some stuff that you'll need for your homework right now, which is some of the limit laws, some of the rules for dealing with limits, and they should remind you of stuff that you learned back when you first learned limits. All right, so limit laws, but now this is in the context or language of sequences instead of functions. So let's suppose that we have two sequences, an converging to L, and some other sequence of numbers, Bn, converging to, say, M. Then we might be asking ourselves, what about the sum? So let's look at the sum, An plus Bn. Let's say I want to add them together and then take the limit. What you'll find here for these limit laws is usually it does just what you hope it would do. So what would we hope the limit of the sum is? The sum of the limits. And indeed, it is the sum of the limits. So that's equal to L plus M. In other words, when both limits exist, you're allowed to just interchange the limit with the sum. That's exactly what I did. And in fact, the same works if you subtract. So I'll just put a minus sign under here if you're subtracting two numbers and taking their limits. Let me just point out that it's crucial that you need both of these limits to exist. So for a quick counterexample, if the limits don't exist, what if an equals n and bn equals negative n, right? So then an plus bn is n plus negative n, which is 0. But an goes to infinity, bn goes to negative infinity. So the sum of the limit of the sum exists. The sum of the limits, you're not allowed to add infinity plus negative infinity. That's totally not allowed. So you can't even do it in that case. So, any questions on that little counterexample? That makes sense? All right, yeah, I'm just wanting to point out why you need the limits to exist before you try to interchange the limit and the sum. And same works for multiplication as well. So the limit as n goes to infinity of an times bn, again, does what you would hope. Yes?
I actually do have a question on the limits. So is it possible that you can add limits going from x to infinity and then limit going from x to negative infinity instead of a of n equals positive infinity, b of n infinity?
Okay, yeah, in this case, okay, yeah, I wrote this kind of fast. I'm just letting n go to positive infinity for all of these. And that's usually for limits, you only let the index go to positive infinity. For sequences, you're generally just letting n go to positive infinity. We might have sequences with negative indices at some point, but not for now. It's just yeah, positive infinity. So again, for all these, we're letting the n go to positive infinity, the same limit in both cases. I don't know if that answers your question.
Yeah.
Okay. Aiden, do you have one?
I understand that the limit of the sum and the sum of the limits are two different things, but are you saying because the sum of the limits isn't possible, are you also saying that the limit of the sum isn't possible, or are you saying the limit of the sum is 0, but there's no way to calculate the sum of the limits?
Yeah, that right. Yeah, what you just said. The limit of the sum exists. The sum of the limits you're not even allowed to do here. So if in the case that the limits of the individual terms doesn't exist, you are not allowed to apply this property. And this is a counterexample of that. Does that make sense?
So what you're saying is if we can't, with like the left side of your quick example, a n, a sub n plus b sub n equals n minus n equals 0. We aren't, that's not allowed to be applied because the limits are infinite?
Right. Yeah.
So everything is moved in that example.
Yeah, I was just showing why you need the requirement that the limits both exist, by the way, here. And you know, maybe I should be a bit more careful with my terminology. So when a limit, what I wrote here, by the way, L and M are both numbers, which means in particular they're not infinity, right? We don't, if a sequence blows up to infinity, we say it does not converge, or we say that it diverges. So let me give you that precise definition. So I already defined what it means for a limit to converge, but if a sequence does not converge, we say it diverges. If it diverges and is unbounded, and I'm going to give you that definition shortly, we say it diverges to infinity. Excuse me. So here's a quick example of that. an equals -1 to the n, which is -1, 1, -1, 1, -1, 1, and so forth. Does this limit converge? No, because it never settles down on any particular value. But nor does it diverge to infinity. So this diverges. On the other hand, how about let's do Bn equals n. So this is the sequence 1, 2, 3, 4, and so forth. This one also diverges. And because it's not bounded, there's no number that it's always below, it actually diverges to infinity. So let me finish off with these limit laws that we need. And again, the point that I'm trying to impress is you need to, these two conditions both need to hold before you can apply these limit laws. And both L and M are just numbers. This is a number. L is a number, M is a number. And when the two sequences both converge, this converges to this number, this converges to that number, then we can also interchange the limit with the product. So this is L times M. just what we hoped we could do, just what we would like to do, and as long as they both converge, you're allowed to do it. Anyway, there's lots of little counterexamples you could come up for these for when the limits don't exist. But I guess I just better, in the interest of time, I better just finish giving you guys the other limit laws. So if the limit of the bn's is not 0, then you're also allowed to divide. So an over bn is L over m. And finally, if c is just some number, then the limit as n goes to infinity of c times an is just c times the limit. So again, just what you would sort of hope it would be. Now, I use the term bounded, which I just erased, but let me give you that definition. So we say a sequence A sub n is, let's first do bounded above. If there exists a number, let's say, how about A in R, such that an is less than or equal to a for all n. We say a sequence, I should, for correct notation, I should probably put this little curly brackets. And we say a sequence an. That's, by the way, what that's usually the proper notation. If you're referring to a sequence, you use the curly brackets. If you didn't use them, it usually means you're talking about a term of a sequence, but that rule is not hard and fast. So to be consistent, let me use the curly brackets here. We say a sequence is bounded below if there exists some real number such that an is greater than or equal to b for all n. Finally, if we just say bounded and we don't say above or below, that means it's both bounded above and bounded below. So if these are the terms of your sequence, bounded above means there's some line that it never goes above. Bounded below means there's some line that it never goes below. And bounded just means it's both bounded above and below. So bounded sequences are nice. Like they have nice properties that we like. For example, let's see, back with my example of that sequence that converged to 1. Or in fact, let's just look at an example of any sequence that converges. Let's say, I don't know what the terms are, maybe they bounce around, but eventually they converge to this limit L. Well, guess what? If the sequence converges, it's automatically bounded every time. So theorem. Convergent sequences are bounded. Which, I mean, it kind of makes sense. Like, if it converges, then it can't really bounce around too crazy. as you can see, if the fact that it settles down really close to this line, it can't be like bouncing up arbitrarily tall or arbitrarily small. So I won't prove that. I could, but I don't have time. No, yeah, I totally could. Just pick like epsilon equals 1 or something. So you might ask the question, okay, if it converges, then it's bounded. Does it go the other way? If it's bounded, does it converge? What do you guys think? Just because it's bounded, does that mean that it converges? No, I did a counterexample for this already, actually. Okay. Anyone remember? It was one of the examples I already did. It's bounded, but it does not converge. The alternating, the -1, 1, -1, 1, is bounded between 1 and -1, for example, but does not converge. An important theorem in analysis, which is pretty elementary, which we won't do in this class, is that, okay, let's say you have a bounded sequence. It might not converge, but it guaranteed has a subsequence that converges. I'm not going to go into that right now, so you don't have to worry about what I just said, but I will. Here's what I will tell you. Here is another criterion for when being bounded does imply you converge. But before I tell it to you, I need to give another definition. So AN is monotonically increasing if each term is bigger than the previous term. Right? So that means the terms of the sequence are progressively getting larger and larger. The graph is always going up, in other words. Similarly, AN is monotonically decreasing if the terms are getting smaller. So that's when AN plus 1 is always less than the term before it. A note about terminology, we don't always use the word monotonically, so I'm just going to put this in parentheses. Sometimes we just say decreasing or increasing. So if I just say that a sequence is monotonic, that means it's one or the other. It can't be both, not according to that definition, but it's either one or the other. And here's the theorem that I was going to tell you for when we do get convergence for a bounded sequence. So let's suppose we've got an increasing sequence. So like each term's getting bigger and bigger and bigger. You can imagine you're walking up a hill. But there's a certain elevation that you never pass. In that situation, you're guaranteed to converge. So, theorem. So if you're increasing and you're bounded above, then you converge. And in fact, here, let me, so I don't have to rewrite this. If it's, thank you. If it's decreasing and bounded below, it also converges. So if it's increasing and bounded above, it converges. If it's decreasing and bounded below, it converges. Like if you start walking down to the bottom of the ocean, but there's a certain elevation which you never get lower than, eventually you're going to settle down at some certain depth, aka converge. And I wanted to do some examples, but we'll have to save those for next time.